Hello everyone, this is Sarah Said, and in this presentation we'll resume with part 2 of Corpora and Machine Translation from Corpus Linguistics and International Handbook Volume 2. So last time we discussed the development of machine translation as a discipline, and then we discussed the corpus-based tools for translators, in which we highlighted the role of parallel concordancing and translation memories. So in this presentation, we will continue with the more advanced forms of machine translation, which are example-based machine translation and statistical machine translation. So first, example-based machine translation. So, example-based machine translation is often thought as a sophisticated type of translation memories. As in a translation memory, the basic idea is to use a database of previous translations, the example base, which is the example-based type. And the essential first step, given that a piece of translated text is added, is to find the best match for that text. Much of what was said earlier regarding matching in translation memory systems also applies to example-based machine translation. Though it should be said that earlier implementations of example-based machine translation often had much more complex matching procedures, linked to the fact that examples were often stored not just as plain text, but as annotated tree or other structures, often explicitly aligned. Once the match has been found, the two techniques begin to diverge. While the work of the translation memory system is over, in which the translator decides what to do with the matches, in example-based machine translation, the system now has to manipulate the example so as to produce a translation. This is done in 3 steps. The first step is when the source text and the examples are aligned so as to highlight which parts of the examples correspond to text in the sentence to be translated. Next, and most crucially, the corresponding target language fragments of text must be identified in the translations associated with the matches. Finally, the target translation is composed from the fragments so identified. So we can illustrate the process with a simple example. Suppose that the input sentence is number 5, and the matching algorithm identifies as relevant to its translation the examples in number 6 with their French translations. The fragments of text in the examples that match the input are in bold. So the example-based machine translation process must now pick out from the French examples in number 6 which words correspond to the words in bold in English, and then combine them to give the proposed translation. These two operations are known in example-based machine translation literature as alignment and recombination. Alignment. Alignment is similar to the notion of aligning parallel corpora in general, which involves identifying which words in the target language sentences correspond to the source language words that we have identified as being of interest. An obvious way to do this might be with the help of a bilingual dictionary, and indeed some example-based machine translation systems do work this way. However, one of the attractions of example-based machine translation is the idea that a machine translation system can be built up on the basis only of large amounts of parallel data, with lexical alignments extracted from the examples automatically by analogy. And this idea is of interest to corpus linguists, and indeed there is a literature around this topic, particularly on the techniques relying on simple probabilities using contingency tables, and measures such as dice coefficients are also explored. And within example-based machine translation, there is a strand of research which seeks to generalize similar examples and thereby extract lexical correspondences. And this can be exemplified in the example number 7 in the translation from English to Japanese. So from the sentence pairs in number 7, we can assume that the difference between the two English sentences, monkey versus man, those are the only two different words in the sentences, which correspond to the only difference between the two Japanese translations, the two different words in the sentences. So therefore, we can assume that the remaining parts in the two sentences and in the two corresponding translations are partial translation pairs as well. Second, recombination. So once the appropriate target language words and fragments have been identified, it should be just a matter of sticking them together. At this stage, a further problem arises, generally referred to in the literature as boundary friction. Fragments taken from one context may not fit neatly into another slightly different context. And an example of these issues of boundary friction is of gender agreement, in which we find in the example illustrated in the slide that the agreement between the noun and the verb is confused by the machine when transferring the extractions into a different context. Another problem is that the fragments to be pasted together sometimes overlap. Like in the example, the operation was interrupted because the blank was blank. The second option is D, so we have an overlap in the use of the word the and because. A number of solutions to these two difficulties have been suggested, including the incorporation of target language grammatical information, which itself might be derived from a parallel corpus, or of more interest to corpus linguists, a model of target language word sequences, or matching the proposed target sentence against the target side of the bilingual corpus. Now moving to statistical machine translation. So, the statistics-based approach to machine translation makes use of no traditional linguistic data. The essence of the method is first to align phrases, word groups, and individual words of the parallel texts, and then to calculate the probabilities that any one word in a sentence of one language corresponds to a word or words in the translated sentence with which it is aligned in the other language. An essential feature is the availability of a suitable large bilingual corpus of reliable translations. The idea of SMT is to find just the T, which is the translated text, that maximizes the probabilities. This probability is seen as a function of two elements. One, a set of most probable target language words given the set of source language words, which makes up the sentence, and the most probable order in which that given set of target language words might occur. These two elements are referred to as the translation model and the language model. Both are computed on the basis of the bilingual corpus. The translation process in statistical-based machine translation, therefore, consists of applying the translation model to a given source sentence to produce a set of probable words, and then applying the language model to those words to produce the target sentence. However, since there are different probabilities involved, this is not a straightforward calculation because the different probabilities interact. And first, we'll start with the translation model. The translation model is the set of probabilities for each word on the source language side of the corpus that it corresponds to or gives rise to each word on the target language side of the corpus. The hope is that for words which are translational equivalents, the probabilities will be suitably high. One problem arises for this approach is that, as all linguists know, there is generally no one-to-one correspondence between the words of one language and another. For example, French translations of adjectives in English have different forms depending on gender and number agreements. Homonyms in one language will have different translations in the target language. Importantly also, some single words in one language may be translated by a string of words in the other language. For example, the single word implemented in English may be rendered in French as mise en application. So, calculating these word probabilities in the translation model takes place through different models of word alignment, such as expectation maximization algorithm and IBM models. The second model is the target language model. The aim of the language model is to predict the most likely sequence of target language words chosen by the translation model. To some extent, word sequence is determined by the translation model, but the language model is necessary to ensure that the target language specific features such as agreement and long-distance dependency not easily captured by the translation model are covered. So the target language model essentially models the probabilities of sequences of words. So just to recap, we start with the target language words in the translation model, which look most likely to be part of the solution. Then we see how these choices fit with the language model. And in a systematic way, we keep trying different combinations until we cannot improve the overall score anymore. And this is so-called decoding stage of statistical machine translation. So to complete the statistical machine translation system, we need a program which can apply the translation and language models to a given input text. That is to search for the target text which maximizes the probability equations. This part of the process has come to be known as the decoder. So one of the common problems in the decoding process is that an exhaustive search of all possible combinations is impractical. So a stack search simple hypothesis, for example, is suggested to take the most probable word-by-word translation in the order of the source text and explore the surrounding search space in a motivated way until the score cannot be further improved. A variation of this approach is a beam search, and in this case, the target text is built up left to right by expanding the translation hypotheses. So these two hypotheses are just proposed solutions for the problem of the impracticality of an exhaustive search for the decoding process. Early on the history of statistical machine translation, simple word-based models are applied. So single words in one language are translated as multi-word phrases in the other language. And this leads to the target language syntax to be significantly distorted with respect to the source language, which often causes bad translations in simple statistical machine translation models. And we can see here in the example of the translation from German to English that the translation led to a distorted target text structure. Like the translation of the sentence in German is "that is to the matter not appropriate." And this is a distorted English structure, while the target text should be "that is not appropriate for this matter." So this led to new applications in SMT. To address these problems, variations of the SMT model have emerged which try to work with phrases rather than words, and with structure rather than strings. So first, phrase-based statistical machine translation. The idea behind phrase-based statistical machine translation is to enhance the conditional probability seen in the basic models with joint probabilities, such as phrases. Because the alignment is again purely statistical, the resulting phrases don't need to correspond to linguistic constituents. And this approach has achieved higher accuracy for translation between languages with different word orders. A variety of models have been applied in the phrase-based statistical machine translation, like the alignment template approach, which takes the context of words into account in the translation model, and local changes in word order from source to target language are learned explicitly. First, the word alignments are calculated in the usual way. Then potential phrases are extracted by taking word sequences which line up in both the English and Spanish phrase alignment, as illustrated in the example in the slide. So, each probability can be calculated based on the relative co-occurrence frequency of the pairings in the rest of the corpus. And this calculates how common phrases co-occur in the rest of the corpus. Then, it moves to identify further phrases, which are called further phrasal identifications, as it keeps reordering phrases until it reaches the most accurate match to the source language meaning and the target language structure. This process continues, each time combining contiguous sequences giving the phrases different structures until it gives different matches to the whole sentence. As the phrases get longer, the probabilities get smaller as the frequency in the corpus diminishes. So a number of scholars evaluated these variants of the phrase-based statistical machine translation approach and found that they all represented an improvement over the original word-based approaches. Furthermore, increased corpus size had a more marked positive effect than it did with the word-based models. Secondly, structure-based statistical machine translation. Despite the improvements, a number of linguistic phenomena still prove troublesome, notably discontinuous phrases and long-distance reordering. To try to handle these, the idea of syntax-based statistical machine translation or structural-based SMT has developed, benefiting from ideas from stochastic parsing and the use of tree banks. Douglas in 1998 developed a hierarchical transduction model based on finite state transducers using an automatically induced dependency structure. An initial head-word pair is chosen, and the sentence is then expanded by translating the dependent structures. Proposed model by Yamada Knight 2001 is tree-to-string model. It uses a parser on the source text only, so the tree is then subject to reordering, insertion, and translation operations, which are all based on stochastic operations. Gilda in 2003 proposed the tree-to-tree alignment model in which subtree cloning was used to handle more reordering in parsed trees. That's all for Corpora in Machine Translation. Thank you for your patience and attention.